Welcome, guys. Today we are going to be discussing on simple equations on capacitors and electrostatic. There is an exercise we have to solve, but before we do that, we ought to understand some basic equation to use so that those equations will not be just foreign. I remember in our last video, we discussed some of these equations, such like we talk about force of attraction or force of repulsion between maybe positive charges or negative charges, which is we have number one, we have something like force is equals to our constant, which is K, Q1, Q2 over R squared. We talk about this, let's call this equation 1. And also, we move further, we talk about that um, electric field intensity is equals to force over charge. Let's call this equation 2. We discussed about this. If you have forgotten this, please let's refer to the previous video. Then in constant time, we talk about potential difference V is equals to potential difference V is equals to work done over charge. Note this as equation 3. Elaborate more on this potential difference. It means that if we have something like, we know that work is equals to force times distance. Normally, work is equals to force times distance. So therefore, and in our equation 1, we have what work and force is, and our D can also, we know that, let's call this equation 4. We also know that our R is same thing as distance. So therefore, let's fix this in equation 3, that potential difference or the potential is equals to force times distance all over Q. And if we take this, let's expand it more, we can also have our force, which is Q over R squared multiplied by Q times D. I believe we got this. Multiplied by D. Yes, I believe we got it. Now, let's interpret this. It means that the constant KQQ R squared, all these KQQ R squared give the birth of this particular force, which we have this. So our D over Q, which is the same as D over Q here. So let's cancel something here. 1Q cancel 1, and 1 R, this is R squared, cancel 1 of the D, just the D. So therefore, our potential can now be KQ, which is K, which is our constant multiplied by our charge, divided by our D, which simply means a distance. Our R can be what? So therefore, we can also say that our R is something as our distance. So that is that. Now, at this point, let's call this equation 5, because we have equation 4 here. That electric fuse is equals to electric intensity multiplied by area. And according to Gauss law, which we talked about in our previous video, we say that Gauss law actually gave us that charge over permittivity naught. This permittivity is also a constant. This is also according to Gauss law. So it means now at this point, let's call this equation 6, and let's call this equation 7. Now, according to this, we can actually say that our E dot naught, our electric intensity multiplied by area, is also equal to Q over permittivity naught. Permittivity naught. Because if electric fuse is equal to electric fuse, so this is also equal to this. With this point now, let's make E the sort of formula here. Divide both sides by A. So therefore, we can have it that our electric intensity is equals to Q over E naught. Then we have our area. So let's call this equation 8. Now, at this point here, let's compare two equations together. Because this physics is all about comparing equation, and do not misplace any of them. So let's compare equation. Let's compare equation 2 and equation 3 and see what we can get from here. Now, when we take equation 3, we take equation 3 as we say that equation 3 we have V E is equals to force over Q, right? So and therefore we have our force, the same force here. Let's bring it here. The same force here, we have our force to be K Q over R squared. K over R squared. Our force brought about K over what? Over R. That's our force. Then divided by, which is divided by the Q. You see, that means all of this is the force which we have, a Q over R squared. All of this is over. Then we also have divided by Q, this Q. Then at this point here now, at this point, this should be equals to Q over R squared multiplied by 1 over Q. Q, we take away this particular Q. So we have what is left. What's left here? We have our E is equals to KQ over R squared. KQ over R squared. That means our constant multiplied by the charge divided by R squared. So V, let's keep this aside. We have our equation to be V is equals to KQ over D. So now we want to compare these two equations. I said it before now. I want to compare the electric field intensity and the potential difference. We got our electric field intensity. Let's look at electric field intensity here. E is equals to. Now, at this point, E is equals to. I want to split this one. We can have it as KQ over R. Or representing, since we have our R is equal to D, representing it as our D squared. So we can then make it that 1 over 2, 1 over D, meaning K, which is our K, our Q, which is our Q, then divided by R squared, which is D times D, right? So if you look at this now, all of these can be replaced by V. All of these can be replaced by V because our V is still the same thing here. So therefore, our electric field intensity is equal to V over 1 multiplied by 1 over D. So therefore, our electric field intensity is also equal to V over D. So let's call this equation 9. Now let's also discuss on our capacitor. You see our capacitor here, we know that the capacitor is a device used in storing charges. Our formula for capacitor, we say we have charge is equals to CV, which is the capacitance. This capacitance here is our constant, and the charge here, the V here is the voltage. So charge is equal to CV. There we have a formula that we call this surface sphere. The surface sphere, which look like something like this, is equals to charge over area. Please let's take note of this. I wish let's begin to call this equation 1 because under the capacitor, and we can now relate it to the electrostatic which we have been discussing. Electric intensity E is equals to surface density over permittivity naught. Now, we want to relate these formulas together to see what we were able to eliminate on this point here. On this very point here now, let's assume that we have our, let's call this equation 2 and let's call this equation 3. We have our E, which is electric intensity, and our surface density here is same as Q over A. At this point here now, let's split this one. I will say surface density over 1 multiplied by 1 over E naught, which is same thing, 1 multiplied surface density multiplied by 1, we're going to get surface density, 1 multiplied E naught, we're going to get this. So at this point here, we can actually say that whatever is our surface density, which is Q over A multiplied by 1 over E naught, which is same thing as Q over E naught, then A. I believe this. So this is, let's call this equation 4. Now we have a formula. Let's look at this formula here. We have a formula that says that E is equals to V over D, which from equation 9, right? So therefore, making our V the sort of formula here, we're going to have it as our V is equals to ED. Our V is equals to ED. Let's call this equation 5. At this point here, let's substitute our equation 4 into equation 5. Can now have it that our V is equals to, what is our E? Our E is all of this, which is this. We have Q over permittivity naught multiplied by the area multiplied by our D. By our D. So therefore, instead of there's nothing common here to cancel. We have our V is equals to Q D over E naught A. So let's substitute this equation 6 into equation 1 because we have something common here. So therefore, we can actually say that making C the something of formula here, we have C is equals to divide both side by V, we have it as Q over V. Therefore, let's split it the same way. It says C is equals to Q over 1 multiplied by 1 over V. So therefore, wherever we see our V, we are going to substitute it to this. You see this equation 6. So therefore, C is equals to Q over 1 multiplied by 1 over all of this. So at this point here now, we cannot just bring it down. So therefore, we will take the reciprocal. So whatever is our QD comes down, let's take away this. Our QD comes down, our E naught goes up, which means here we're going to have E naught A over what? QD. So therefore, Q, we cancel Q. So our capacitance, which is therefore equals to, we have E naught A over D. E naught A over D. Now, at this point here now, this particular equation 10 actually proves something here. It proves that as the capacitance increases, the area also increases. As the capacitance increases, the distance between the plates also what? Decrease.